Sorry I didn't get the first part of the recording.
This is frozen.
Thank you. Okay, so guys, pictures are going to be huge for all of these, by the way. Sometimes it's kind of hard to draw the scenario, but at least give it a shot. And so we have this rectangle, we have width times length. So our area is just length times width times length. Okay? And then it says the length and width are changing. Obviously, in that case, the area would be as well. So dA dt is representing the change in the area with respect to time. Okay? Equals, what's the derivative of L with respect to time? dL dt times what? Don't forget, times W plus L times dW dt. In other words, there's a little product rule right there, right? What? Oh, and so just note, if I said, hey, how fast is the area changing? In order to solve this, you would need to know all four of those, like something. We couldn't have more than one variable in our equation, so we would need to know all four of these. And what I mean by that is maybe we have a ongoing rate of change of the length and width, but do you see how this is also dependent on the size of the rectangle? Interesting, right? Have you guys ever blown up a balloon with your mouth?
Yeah.
You haven't? Go home and do that. That's your homework.
She pranked him.
So think about how as you blow, obviously the volume is getting bigger, the radius is getting bigger, but sometimes as you blow, it gets easier. Have you ever noticed that? Like that first blow is those first few are harder. So you could maybe even do like change in pressure as we change the volume, or change in radius or change in pressure as we change the radius. And that depends. Like if my radius is teeny, the pressure is high, and if my radius is bigger, the pressure is maybe lower. And then it starts to come back again. Like as you get really big, it's harder to blow air in there. Does this make sense? So there's often a dependence on this current state. Okay? All right. Spherical balloon. I'll try to get out of your way again. Relate the rate of change of surface area to the radius. So dA dt. Oh, and here's a good reminder. AP doesn't give you formulas, do they?
Oh, no.
Sometimes. That's true. They do sometimes.
We had a physics
On this
formula
one, I
sheet.
feel like they probably would.
I think you're right. They probably would. Remember that pi is a constant. So this is 4 pi. And then what? What's the derivative of r squared with respect to time?
2r dt.
Nice. Good.
Good job, guys. Plus.
Okay, so then simplifying this would be 8 pi r dr dt. I guarantee you, we will, but also r's will come up. So dr dt is kind of a frequent one. All right, cylindrical tank. It says relate the rates of change between the water level and the volume. So dv dt equals... by the way, it says cylindrical tank, which means what is true about the radius? It's a constant, right? So do we need to take the derivative of the radius for a cylinder? No. If it's a different shape, then yeah, potentially we do. So pi r squared is a constant. And then we have dH dt. How'd you do on those three? Any questions on them? Okay. I told you to look at 6 And actually, let me give you 1 minute to give 6 a try.
Which ones are we doing?
Just 6 right now. Good try.
No drink.
It is like in Clash Royale, bro.
Are you super happy that you get your favorite class for Halloween?
Yes. I'm super happy every day you guys are here.
I'm not gonna be here.
Wednesdays are rough.
I'm not gonna be here tomorrow.
So now I'm even happier.
Yeah.
Not really.
Because I'm not gonna be
Oh, I'm sad.
Listen, I'm gonna miss the 6th or 7th.
Good.
But we only have class the 6th.
What are you going to be doing, by the way? Are you doing state?
here.
Yeah?
But I'm not ready.
You're just going?
I'm
No,
slow.
you're
I'm
not.
just cheering.
You are not slow.
What about me?
I don't know.
Are you gonna ask what I'm doing?
You're going to be in here.
No, I promise. Well, tomorrow I am, but like the
Right.
6th and the 7th, I'm seriously missing.
Okay. Who cares?
Oh.
No, what are you doing for real?
Oh my gosh.
If you say something 6 and 7,
On the 6th, I'm going to the Broncos Thursday night football game against the Raiders.
oh, that'll be fun.
On the 8th, I'm going to the Nuggets game. On the 7th, I'm going to Casa Bonita.
What did you say?
Yeah. All right. That sounds fun. I'm glad for you. Good job. Okay, so this rocket is shooting up, and an observer, it says on the ground, so we will model this like a right triangle. But this one is not Pythagorean theorem. Why?
Change an angle.
Yeah, so maybe call it theta. That's our usual. So the angle of elevation, remember, is between the horizontal and looking up at the object. And so obviously we're looking kind of horizontal at it when it's about to launch, and then as it goes up, our angle is changing. And that, of course, depends on the speed of the rocket. So I might call that rocket's height h, and maybe how far away from that rocket we are, x. What relates those three things?
Oh, time.
Tangent of theta equals h over x. Good. Is the observer moving closer or farther away from the rocket?
He's not.
No. So if we say we need rates of change in here. Right now it's just a length and angle relationship. We need rates of change. How do we do that? Okay, so this is secant squared theta. Then what? Nope.
Oh,
Nope.
times
There
theta
you go.
Nope.
times 1.
Derivative.
Derivative of theta with respect to time, right? So d theta dt. Okay, x is constant, meaning this guy's not going to walk closer or farther away. So 1 over x, and then dh dt. So now we have a relationship between the change of the angle and the rocket's speed. Everybody see that? In fact, on yours, maybe note that this is the rocket's speed. Okay, I'm going to tell you, these problems are really being clear about what you're trying to relate and not so much giving you real-world information. This problem would, if it was going to be one you had to solve, which is obviously our goal, it would say something like like the whole observer thing is fine. An observer is watching a rocket take off. The rocket is flying or launching, whatever the word would be, at 200 feet per second. I don't know, like some rocket speed. What is the rate of change of the angle of the observer? That's how this would sound. It's not going to tell you how to set it up as much. Okay. I don't want to do 7, just read it. It's just another version of weird scenarios that are changing with respect to each other. So we have a boat on a dock or being pulled towards a dock, right? Like here's our water, here's our boat,
Oh,
right? We're pulling the boat closer to the dock using the rope. It says the pulley is higher than the boat's bow by several feet, so I probably drew my dock too short. Okay. There's that right triangle. Relate the rate that the rope is hauled in with how fast the boat is approaching. Okay. These are interesting. Do you agree? I hope you do.
Yes,
Let's get into solving some.
that's Calc.
Go flip to 4 or 5, please. I want you to, I don't know if you want to write these down. I like these steps better than what are in your packet. I will post these today. So let's just talk through them. If you want to try to write really fast, but I'm not going to wait. You can do it at home. Okay. Draw 2 pictures. One, generic relationship. That's what we've been doing so far because we have not been given specific moment pictures yet, or information rather. So we've only been drawing generic pictures. That's this whole last section was. So we're going to start by drawing a picture that represents the situation or scenario and the parts that are always true. Like maybe our radius is always 2 feet. Maybe the height of the light pole is always 25 feet, whatever. And then we're going to draw another picture that's the same picture, only with information specific to the moment they ask us about. Like maybe we're walking away from the light pole and we're currently 50 feet from it. So we would add that information, that kind of thing. Okay, step 2, we want to identify our goal. Like what are we trying to find? Are we trying to find d theta dt like we just were? Or are we trying to find dh dt? Maybe we're trying to find the speed of the rocket because we can measure the speed of our angle changing. Okay, step 3, maybe put a star by that one. It's absolutely the hardest step. Figuring out how the stuff relates together. I put that it will require some creativity because sometimes it's like, what the heck? How does this even relate? Okay. Did you guys ever feel that with the Ferris wheel problems in pre-calc? Like, what the heck is going on? That's how it's going to feel sometimes.
there's one on the test that I was like that.
Yeah.
You measure like sine wave of a guitar string.
Oh, okay. Interesting. Yeah, that sounds kind of weird. Okay, so the last section that we just did, we've been working on steps 1, 2, and 3. With the exception of we didn't draw the specific moment picture because we weren't given information to do that. But steps 1, 2, and 3, that was section 4.4. And then going forward, actually we did step 4 too. We had to differentiate to make it a rate problem. And I put that reminder, don't forget the chain rule. So that was where we did things like dx dt, d theta dt, etc. Okay, steps 5 and 6 is where you take the information given from your specific picture from your the problem's prompt, and you start plugging it in to solve for the variable. So 6 steps. If you use this structure, it's going to help. Okay. I see some of you writing, which is good. Like I said, I'll post this. Okay. We're going to try it with a couple easy ones, and then we'll try to get on to some better ones. Well, we'll see. This is taking longer than I thought it would, which is okay. This is important stuff. No, it's not your fault. This is important. Those steps are what I'm going to use instead of these. These are not bad. If you want to use the ones that are written in your note packet, that's fine. So it's not like they're bad steps. I'm just using the ones that I just showed you. Okay. The top of that is just practicing taking an implicit derivative with respect to time and plugging in numbers. Do you feel like you need to practice that, or do you want to get into the actual problems a little bit? What do you want? It's okay. We can do it if you want. Do you need it? What? All right, nobody's saying. Let's try a rectangle. We can go back to that if we need to. I keep wanting to set this down and right, but okay. Guys, this is taking the rectangle one from, I think it was number 2 that we just did. Okay? It's taking that scenario and now making it a related rate problem. The width of a rectangle is increasing at a rate of 2 centimeters per second, and its length is increasing at a rate of 3 centimeters per second. Okay? Maybe you're like stretching a rubber band around a rectangular box or something. That's this. Okay? We're stretching it out. At what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5 centimeters? So this is dependent on how big the rubber band is or whatever we're stretching. So let's follow our steps. Step 1 is 2 pictures. Okay, that's the generic. That will always be true. Width and length, right, of a rectangle. Like this one has very limited information that we're worried about. That's the general or generic picture. Specifically, so specific picture, we are told the width is 4 and the length is 5. Therefore, at that moment, the area is 20. We may or may not need that, but we might as well put it in there. So general picture and then the specific. Okay, that's step 1. Step 2. I'm going to number these with little circles. Step 2. What's our goal? And I want you to write this. You can write it in English first, but then make sure you convert it to calculus so that you can see it in your equation. What are we trying to find? dA dt. You guys see that? It says, at what rate is the area? That's dA dt. Step 3. Here's the money step. We need a relationship between them. Well, in this case, it was pretty easy. A equals length times width. Okay. Step 4, differentiate dA dt. And remember to do the product rule. So W dL, that doesn't look like you know. dL dt plus L dW dt. Please stop me and ask questions if you're not following. You need to be following 100%. Sure. Can you have someone else do it since you're like... Thank you, Ocean. Step 5. Evaluate at a point, right? Or like we're plugging in our information to solve. What in here do we know? We know the length and width and what? dL dt and dW dt. Do you see how all that was given? In fact, maybe if it's helpful, go up here and say, hey, this is dw dt. It's the rate of change of the width with respect to time. And this one is dl dt. So go label those if that helps you see it. In fact, I would recommend doing that. Okay, step 5. I'm going to try to carve out some room here. Step 5 looks like this. dA dt equals, what is W at this moment? 4. What is dL dt? No.
3.
3.
Sorry, gang. Sorry, everybody.
What is length at this moment? 5. What is dW dt? 2. Okay, and then 6, step 6 is just to solve, like just get through the stuff to solve. So 12 plus 10. So 22, and label. So 22 what? Yeah, this is area, so centimeters squared per second. Okay? So let's kind of quickly review what we did. Pictures help you relate the pieces. Draw them. Please, please draw them. Okay? Identify your goal so you know what you're solving for. Step 3 is the hard step. This one it wasn't, but in most cases, step 3 is the hard step. Differentiate to turn it into an actual rate problem. Otherwise, this is all just lengths and areas. That's not a rate. So differentiate, plug in, solve. Plug in at the moment that we're looking at. What do you think? Does that feel okay? Okay, let's try this police car one. Same problem or same scenario. Do you want to do this one?
Not really.
I have better ones. Ooh, that we're not ready for that one yet.
What's it with them and police and speeding cars?
Yeah. I don't think we're ready for the harder ones. But also, I feel like we're past this. Let's do it. All right, police car. Actually, we do need to talk through this one because sign is kind of an important deal. So remember we called the police car's position as Y and the speeding car, the bad guy's position as X. Why did I write a Y? And then we had a D for the distance between them. Okay, let's read. The police car is approaching the right-angled intersection from the north, and the other guys turn to the east. When the police car is 0.6 miles, so that is a location, right? That's important. What letter in our scenario is that? Maybe you could label it. It's Y. Good. And the car is 8.8 miles. Which one is that? Okay. It says the police determine with a radar gun that the distance between them and the car is increasing at a rate of 20 miles per hour. So what is the 20? dt, the change in distance with respect to time. If the police car is moving at 60, what is that? dy dt. What is the speed of the car? Okay, so just to recall, we have x squared plus y squared equals d squared. Actually, we have a picture, and then let's follow our steps. I should have not done that yet. Specifically, we have 0.6, 0.8, and then dt is 60. Sorry, is 20. Now, over here we also know that the police car's moving toward the intersection at 60, but what should we label that? Think about this now in like a math context. If we're speeding this direction, am I going to, what am I plugging into the equation? Negative, right? Okay. All right, everything's set up. Step 3. Actually, no. What's our goal? Step 2.
Come on, man.
How fast is the car going away? What if the car had turned, came in same direction as the police car but turned right? What sign would its information be? Okay. Step 3. X squared plus y squared equals d squared. Step 4, differentiate. Step 5, plug in. What all can we plug in here?
Everything but.
Yeah, it's literally everything but dx dt. But do you see how right now,
Except for
if I plugged in 60, this would be a completely different problem, wouldn't it? Can I just plug 60? No. This thing is going negative 60. That matters. Wait a minute. We don't have a distance.
That's what Devin just said. Out loud. Yes, you did. Why don't you take that here, right?
What do we do? Yeah, can't we just do the Pythagorean theorem
Yes.
to find the current distance at the moment, right? So up here, d equals, at the moment in question, d equals just square root of 0.6 squared plus 0.8 squared. Did anybody recognize that this is a 3, 4, 5 triangle? So what is the distance? Okay.
Dang, you said that without even doing any calculation.
Was it just a lucky guess?
No. I actually saw 64 and 36 in my head and got 100.
Okay.
I was like, "Damn."
Anyway, let's go ahead and solve. 1.2 times 6. What is that? 7. Negative 72. Equals 40. Anyway, can someone finish solving that and let us know what it is? Also, don't forget to label. It's 112 divided by 1.6. Did anybody do that?
Kevin did it.
What is it?
70. Good job, Kevin.
70 miles per hour. Okay. Interesting. Now we can figure out how fast the car's speed is without being in the car, without anything else, right? It's cool. Look at number 6. Go ahead and flip to number 6 in your packet. Here's one of those expanding pool. Okay. Maybe if you look at the problem right before it, it's an ice cube melting. So maybe we're now looking, instead of at the ice cube, we're looking at the pool that it's making on the table as it melts. All right? Why don't you try number 6? The answer is 2. I mean, who cares what the answer is? You still got to do it.
It's 2.
Okay. Guys, on these, the generic and the specific pictures, they don't really change that much because we're only dealing with one dimension, right? Which is the radius. So I want you to get in the habit of doing it, but it's not like these necessarily need it. Of course, we're dealing with the area of a circle in this one, which is what? Pi r squared, okay? So over here on the specific picture, pi times 4 squared. And I'm just going to leave it as 16 pi for now. So that was step 1. Step 2. What's our goal? Calculus goal.
dr dt.
Good. dr dt. Step 3, we kind of already wrote this. So it's kind of unfortunate that the examples so far have not demonstrated that step 3 is the hardest step, but that's okay. We're getting used to it. Okay, this time the radius is not constant, right? As the pool expands, we can't, like we did before, we can't say that this is constant. But the pi certainly is. So let's see. Let's do 2 pi r dr dt. Okay, what do we know in that differential equation right there?
I know dA, dt.
Okay, so 16 pi rather. R is 4 currently. And we don't know dr dt. Okay, note that even though I solved for the area at the current moment, it isn't actually in there, which is fine. It's always okay to have extra information. Now, what is the unit for this? What do we label? Well, it says it right there. What the heck?
The answer, guys. Just trying to answer. Inches.
Okay. How'd you do?
We did good on that one, Jeffrey.
Okay.
So, yeah. That's good.
Okay, so in terms of homework, the bell's about to ring, so just listen. Finish on that, on 4.5, just finish 7, so starting on the next problem, 7 through the test prep. Okay? And you guys have in your packet this problem?
Yeah.
So do that one problem as well. It's not a related rate problem totally. So I just want to see if you can figure that one out. And then tomorrow we'll do some more of these, get into some harder ones.